Hello everyone, I'm Vibhor Singh, and today we'll be discussing the 28th problem of the CP-31 sheet under the 1300 rated parameter. So as you can see, this is the CP-31 sheet and the 1300 rated problems have been selected, and this is the 28th problem, good array. Let's call an array good if there is an element in the array that equals to the sum of all other elements. For example, an array A is good as the element A4 is 7, which is equal to the sum of the first three elements, that is 1 plus 3 plus 3. So that's the definition of a good array. You are given an array A consisting of n integers. Your task is to print all indices j of this array such that after removing the jth element from the array, it will be good. Let's call such indices nice. So for example, if A is this, they have given us an example that if we remove index 1, that is if we remove 8, we'll have 3, 5 and 2, and then after that 5 is equal to 3 plus 2. So it is a good array. So this is an example of a nice index. So let's try to understand the problem. Let's use this first test case, that is 5, 2, 5, 1, 2, 2. Right. So first we have the length of the array, that is 5. Then we have the elements as 2. So we have 2, 5, 1 and 2, 2. Right. 2, 5, 1 and 2 and 2. Right. Now what is the problem state is we have to find the nice indices and print them. Okay. Now what is a nice index? Let's see if you look at index 1. So if you have 1 based indexing, if you look at index 1, first thing is we'll remove this index. Okay. So or we'll remove this element from the array. So our new array becomes 5, 1, 2 and 2. Now if this new array is good, then this index is nice that we removed. Now what is the definition of good array? If you look at the first element in this, that is 5, that is 5 is equal to the sum of all the other elements, right? Now 5 could be anywhere in the array. Basically any one index is equal to the sum of all other indices in the array, then the array is good, right? So this is 2, right? So 1 plus 2 plus 2. So after removing this index, our array becomes good. But after removing the element at this index, our array becomes good. So this index is a nice index. Similarly, if we remove this 2 or this 2, one by one, if we remove any of the 2's, our remnant of the array, if let's say I remove this 2, that is the fourth index, my remnant array becomes 2, 5, 1 and 2. And again, we'll have 5 is equal to 2 plus 1 plus 2. That is 5 is equal to the sum of all the other elements. So it is a good subarray. So this is a nice index. So the nice indices that we'll have for this entire array are this, this and this, right? That is 1, 4 and 5. Those are the nice indices. And as you can see, that's given to us as the answer. That is, there are 3 nice indices and that are 1, 4 and 5. So I hope the problem statement is clear to you. Now let's look at the expected time complexity. We are given n goes till 2 into 10 raised to 5 and ai goes till 10 raised to 6, right? So we know 1 second in Codeforces. So 1 second in Codeforces corresponds to approximately 10 raised to 8 operations. We are given n goes till 2 into 10 raised to 5 and ai, max of ai is still 10 raised to 6, right? So anything of the order of n or order of n plus max of a of I, or even order of n log n, maybe even plus a max a of I, this thing is fine. But if we go in something like order of n square or order of n into a of I, then we'll get TLE, right? So that's it. That's for our expected time complexity discussion. That is, we can use order of n, we can use order of a of I, but we cannot have any exponential or any multiplication in the two. So now let's try to solve the problem. Okay. So whatever array we have, let's take the first example that we have, that is 2, 5, 1 and then 2, 2. Okay. So whatever array we have, first thing that we should do is calculate the sum of this entire array, right? Calculate the sum of this entire array and let's call it sum. Okay. For this array, it will just become 12, right? 2 plus 2, 4, 5, 10 and 12. So the sum is 12, right? Now for each index, we have to find that after removing that index, is our array good? Okay. So let's try to form a condition for a good array first. That is, how can I identify a good array? Given some array with some values a1, a2, a3, so on, this array is good. How do I identify this? Okay, so let's say Aj is equal to sum of all other elements. Right, which is some index aj is equal to the sum of all other elements in this array, right? So if aj is equal to sum of all other elements, our condition is held true, right? Right. So let's take this. We are assuming that aj, we are assuming this is a good array and aj is equal to the sum of all other elements. Now what will be the sum of all other elements? Okay, what will be the sum of all other elements? Let's say we have the overall sum with us. Let's say we have an overall sum, let's call it S. Okay. So sum of all other elements, that is all elements except for aj, will just become S minus A of j, right? See, sum of all elements except for aj in the array would be S minus aj, right? Because overall sum is S. So S minus aj should be equal to aj for our array to be good, right? For good array. So from this condition, if we take aj to the other side, we'll get 2a of j is equal to s, or we'll get the condition that a of j is equal to s by 2. So from here we have a condition, or we have the condition that if there is LE element, any ai is equal to overall sum by 2 in an array, then it is a good array. Right. So if any a of I is equal to overall sum by 2, then it is a good array. And if this condition does not hold true, then it is not a good array. Right. Because we have formed this condition through our condition of good array that aj is equal to sum of all other elements. And this is the only condition when it will satisfy. That is aj is equal to s by 2 and s is even. Right. S should be even. Because if s is odd, then like this condition will fail, right? 2 into aj is equal to s. So aj is s by 2. Like 2 into aj should be s. So s is always even. Only then can we have a good array. So overall sum of our array should be even, and there should be some aj or some ai such that ai is equal to s by 2. Then our array is good. Okay. So we found a condition for having a good array, right? This is a condition. This is a very easy condition to identify. That is, I can store all the values in the map, and if some value of s by 2 exists, then I can say that yes, the current array that I'm looking at is a good array, right? Now the only thing that we have to look at is, given the initial array, taking the example earlier, given the initial array, if I remove any one index and then look at the rest of the array, right? I have to remove any one index and look at the rest of the array. So I have sum of overall array, right? I will have sum of overall array, that is sum of all the elements. For this case, it is 12. So when I say I have to remove one index or one element, the sum of the new formed array, that is the array of the remnant elements, what will that become? See, the sum of these elements will just become overall sum minus this index I'm looking at, right? So let's say I'm currently identifying or calculating for index I that whether index I is good or not, whether index I is nice or not, right? So I'll remove index I from the array, and the new sum becomes sum minus a of I, right? Let's call this new sum, right? So I have a new sum which is the sum of the remaining array. I remove the current index and I get a new sum which is equal to sum minus a of I. Now what do I have to see? I have to see that if new sum by 2 exists in the array, then this current index is nice. I is nice, right? If new sum by 2 exists in the array, and also new sum is divisible by 2, right? New sum is even. So these are the two conditions that we'll have, that whatever new sum value we have, that should be even, and if that value, if the half of that value exists in the remnant of the array, then our current index is nice and we can push it into an answer vector or whatever vector we create to store the nice indices. And this is what our solution will be. That is, first we'll calculate the overall sum of the array. Then we'll calculate for each index new sum is equal to sum minus a of I. That is the remnant elements. And then we'll check amongst the remnant elements if new sum exists. If new sum by 2 exists and new sum is even, then our answer would be that we will push this current index into our answer. Okay, this current index gets pushed into our answer. Right. The only thing that remains is how do we make sure that we are not using this index. That is, we are looking only at the remnant of the array. So if we have some case like this, that is, we have two elements and we have 5 and 10, let's say. Okay. Let's say we have something like this. Obviously, we can have more number of elements. We're just looking at a sample case, that is, and 5 and 10, and then we are removing this 5. Okay. If we remove this 5, our new sum will become 10, right? So it is even, and our new sum by 2 is 5, right? 5 exists in the overall array, but it does not exist in the remnant array. So we have to make sure we handle such cases as well, that whenever we are removing an array, whenever we are removing an index, we need to make sure that we are not considering this index while calculating the answer. Now, how we'll do it, let's just look at it through the code. So let's move on to the code of the problem. First, we take n and the a as input. So I've created a vector of counts. So this is the map, right? Instead of having a map, like a data structure map, I'm using a vector of counts that will form the map as me, which is of length 10 raised to 6. So we're given that a of I can go till 10 raised to 6. So I'm doing this because it will be much easier for me. You can use a map as well. Whatever you do is fine. Since it's only till 10 raised to 6, I've done it through a vector. And what I'm doing is, I'm taking a of I as input, I'm increasing counts of a of I, and I am adding it to the sum. So my sum is the overall sum of the array. After that, I'm creating a vector of answers, and I'm creating new sum is equal to sum minus a of I, right? And then what I'm doing is, I'm decreasing the counts of the current element by 1. That is, the current element is removed from my consideration, right? So just specifically to handle this case that we have seen in the end, that I will remove this element, my current I, since I'm removing this element from the array to create a new array or a sub array for which we are looking at. That is why I am removing this element. That is why I'm removing this element from my map over here. Okay, so I'm decrementing the count of the current element, and then I'm making a few checks. That is, if my new sum is even and counts of new sum is greater than 0, and I've put a third condition over here, that is, new sum by 2 should be less than equal to 10 raised to 6. Now, why do I have this condition? See, a of I values can only go till 10 raised to 6. And also my counts vector is only till 10 raised to 6, right? Since I've created the vector, that is why I have to put this extra condition. That is, my new sum by 2 should not be out of bounds of my array, right? There is no chance that if my new sum by 2 is greater than 10 raised to 6, there's no chance of the array of being good, because such a value cannot exist in our array, right? So that is why I have this extra condition that it should be less than 10 raised to 6. Only then check in the array. Otherwise, it will be an out of bound index. So we don't need to check in the array. And if the condition satisfied, then in the answer, we'll push back I plus 1 for one base indexing. And then we are incrementing counts of a of I again. So this is to put back the current element, right? So initially we removed this element from consideration. So over here, we put the element back into our overall map. And then in the end, we are printing the size of the answer and then each index in the answer. So this is how we are printing all the nice indices. So that's it for the solution. Let's look at the time complexity. So taking the input will take order of n time, right? Then running this entire for loop logic over here will also take order of n time, since there's no extra loop, only the loop of I from 1 to n, right? Or 0 to n minus 1, right? And then finally for printing the answer, again we have a loop of order of n. So overall time complexity of our solution will just become order of n, right? There is no extra time. Now, what will be the space complexity of our solution? Also, in the time complexity, actually, we should add this part as well. That is order of 1e6, which is initializing the counts vector to 0, right? So this is n plus 1e6. Okay, and 1e6 is max of a of I, so we can also write it as max of a of I. But right now I'm just writing it as 1e6 because we have hard coded this value right over here, right? And then overall space complexity will also be, so the input vector is of order of n. Our answers vector can have maximum all the indices, so that can be order of n at max, and our counts vector is of size 1e6, right, or 10 raised to 6. So overall space complexity will also become order of n plus 1e6, right? And the reason I'm writing 1e6 separately and not just removing it is because 1e6 actually represents max of a of I, right? So instead of writing max of a of I, I'm just writing 1e6 over here. So that's it for the overall time complexity and space complexity discussions. I hope you're able to understand the solution. Thank you.